Hi, welcome to this GCSE Science Class Notes video on exam practice questions and revision. Today we're going to be having a look at a couple of questions on electrolysis and right and half equations and doing a bit of revision on these. Now there's two types of electrolysis that happen. Aqueous ions is the one we're looking at here, where we have in solution, where we have ions which are dissolved in water, as opposed to the molten state. So it's the aqueous ones here that we're looking at. So let's begin. We've got, here's a typical question. This question comes in many formats. I picked this one because it brings in a lot of skills that you need and revision, of course, that we can do here to answering some questions. So as always, you can pause, fast forward if you wish, or you can just stay with me as I go through this question. Now, my advice, one of your top tips is when it comes to answering these types of questions is have a look at the information, the evidence that they give you. So that's what I'm going to be doing first. I'm going to go through the evidence, break down the question and or break down the evidence that they've given us without even looking at what A, B, C or D are saying. So let's have a look at the picture or the question that they're going to be asking us. Well, let's have a look here. We've got a question on electrolysis. It says very clearly at the top. So we know it's something to do with electricity and splitting a substance, a mixture. In fact, here is sodium chloride. That's what it says, and that's in solution. It's aqueous. So let's have a look. Let's have a look and see what information they've got here. It's an industrial process, of course, so that means they're going to make useful things for selling and for making materials, etc., and things like that. So let's have a look. From the beginning, let's have a look at the overall structure. Let's see what's going on. We'll look at the apparatus first, I guess, the hardware that's in the question. We have first a container. We have one inlet. Look at the arrow going through. We've got three outlets, so three things coming out, one thing going in. We've also got a positive and negative, and encased within that is a solution, liquid, negative, positive electrodes there, and we've got a porous barrier. Porous meaning it lets things go through, and obviously the grey, the grey shading in this picture is a sodium chloride solution. So let's have a look at the hardware first. Let's look at the electrodes. I've got a positive and a negative electrode, and just to remind you, panic is the way to remember which electrode's which. So I've got a positive electrode, P for positive, A for anode, so this is the anode, and then I've got a negative. Negative is cathode, so cathode there. Let's look along. So I've got the electrodes, I've got a porous membrane. That means the porous part of this means things can diffuse one way and the other way as well at the same time. And I think that's it on that front. So let's have a look on. Let's look at the chemicals involved here. So I've got sodium chloride. There it is. Sodium chloride. It's aqueous. It's in solution. It's an ionic compound. Therefore, I've got negatives and positives here. Since it is aqueous, I also have then. Well, let's put it into the grey area. So we've got on this side, if I write chlorine, and this side sodium ion. Sorry, chloride. I should have said there. But also, if it's an aqueous solution, we know that water dissociates into H plus ions, but also OH minus ions. That's why the pH of water is neutral, because I've got equal amounts of these two ions present when a small amount of water dissociates. Okay, so we've got the chemicals sorted out. Oh, no, I haven't. Look at the top. I've got chlorine being formed. So I'll just remind myself that it's Cl2 because it's a halogen. It's diatomic, and I've got hydrogen, which is also diatomic. There it is. So I've got these, and these are gases, of course. So let's put the state symbols in as well while I'm here. There they are. Everything else is aqueous. That's it. So the chemicals are sorted. So let's have a look. So what's going on? So it looks like that when I pass electricity, I have a potential difference between the positive and negative electrodes here. The chloride ions turn into chlorine, of course. I can write an equation for that. So turn it down the bottom. Maybe let's start doing that. So chlorine goes to chloride, goes into chlorine. There it is. And half equations then, the redox part of this, is looking at oxidation reduction. And if we think about what that means, we talk about oil rig. That helps us remember that oxidation is loss of electrons, while reduction is gain of electrons. And here, that's precisely what's happened. Look, the chloride has lost its electrons to become chlorine gas. There are the electrons. So let's have a look at this equation. Is it balanced? First of all, no, it's not. I can see straight away. I've got 2 Cl's here, only 1 here, so let's balance those. I've got then the overall charge on this side before the arrows -2, because 2 times -1 is -2. It's -2 here. Here I've only got, well, 1 times 1 minus, only 1 minus here. So I need to balance the charges. And the only way I could do that is by adding a great big 2 in front of this. So 2 times 1 minus is 2 minus. Balance. So that's a balanced redox equation, which is happening at the positive electrode, or be precise, at the anode. And then let's have a look at the other side, what's happening here. So H plus ions have gone to hydrogen. So let's have a look. If we write that here, so H plus goes to hydrogen like that. Oops, a bit of an overzealous 2 there. Let's get rid of that. And we've got hydrogen, again, diatomic. So what's happened here? Well, obviously, the H plus ion has gained electrons. So we should write them here, I guess. There we go. There's the 2, well, electron there. And let's have a look at balancing this then. I've got 2 H's here, 1 H here. So a great big 2 here. Then that's it. On the species, no more ions or elements. So now I've got overall charge before the arrow. I've got minus plus 2 plus, therefore the overall charge on this side is plus 1. Here it's 0 because elements have no charge on them, so there is no charge on this one. Therefore I need to balance this. The only way I can do that is by adding another electron there. Okay, so now we've got balanced everything here. So 2 times 1 minus is 2 minus, 2 times 1 plus is 2 plus. Put that in your calculator. 2 minus plus 2 plus, I get 0. So all balanced and happy. Oh, forgotten the state symbols. They're very important here. I've got gas being formed here, and this is going to be an aqueous in solution. Down here again, chlorine is a gas, and the chloride is aqueous. Very important to make sure you write those things down. Also then I've accounted for, well, let's have a look, the H plus ions. I've counted for the chloride ions. I've got sodium chloride hanging about. Okay, so that's what's left over. Now, as the H plus ions have gone down in solution, the amount of H plus ions have decreased. So H plus ions are acidic. What I've got more of, or a higher concentration of, is the OH. Therefore, the resulting solution, X, then must be sodium chloride, but sodium hydroxide, sorry, sodium hydroxide, because that's the 2 things that are left over. And because I've got a hydroxide, therefore its pH must be greater than 7. So it's an alkali solution. Okay, so I've decoded this question. Let's go and have a look. And there's nothing else I could break down here. Let's go and see what the questions were. Looking at the questions, why do the chloride ions move towards the positive electrode? Well, straight away we can see that chloride ions have a negative charge. The positive electrode's obviously positive. So there's some sort of attraction there. Write the chemical equation at the anode. We've already done that. Now breaking down the question or the evidence. Write the chemical equation at the cathode. We've done that also. And explain why the pH, or why is the pH of the solution high? So why does it have a high pH value? We've already talked about that as well. So answering these questions, electrostatic attraction between oppositely charged ions cause this attraction. And there's the first half equation. There's the second half equation for our redox. And then last but not least, high concentration of base or alkali, OH minus ions. Therefore, the solution is alkali. Useful products from this: chlorine gas can be used in bleaches, etc. Hydrogen can be used in the process of, let's say, making margarine, but it's also a useful substance in chemical reactions as well. Then you've got sodium hydroxide, which is also very useful to sell to make products as well. Over to the second type of question we've got here. Here I'm looking at, again, aqueous ions in solution, but this time we're looking at copper sulfate. Now, let's have a look here. You can pause the video again. There's bits of evidence here and some questions. It's up to you if you want to stay with me. Then I'm going to move on to the next slide. So let's decode or break down the evidence that they've given us. Well, let's see what we've got. We've got investigating the electrolysis of copper sulfate, it says, and it's a solution again and was carried out as shown. So we've got some apparatus, some hardware here. We've got the container, of course, and then we've got the positive electrode, negative electrode. And just for the sake of it, let's just go over a bit of revision again. Don't panic. Positive anode, so that's the anode. This is going to be the cathode. I've got again, so we've got a potential difference when I put this, connect this to a cell or a socket in the wall. And then I've got this grey solution, which is a copper sulfate solution. We'll come to that in a minute. There's carbon electrodes, right? Why carbon electrodes? Well, because carbon is not going to react that much, so it's inert. So it doesn't take part in any chemical reaction. Okay, we've covered all the hardware. Let's go inside then. We've got the chemicals. The only chemical we really have is, well, copper sulfate. Now, in any GCSE exam question, they will give you the formula of copper sulfate. It'll be this. The sulfate part is is 2- overall, and copper is 2+ in this case. Right, we've got this here, but also remember, because it's a solution, we've got to remember that we're going to have water. Therefore, small amounts of water will dissociate or break down into OH- ions and H+ ions. So we've got that mixture here. I flick the switch, I get then something being formed at the negative electrode, so that's the cathode, of course. I get a solid formed. So the solid of what? Now we've got copper 2+ as a metal here. That's going to migrate or be attracted to the cathode because it's negative. We're going to have a chemical reaction going on there. So let's write it here. So C for cathode, and the chemical reaction then will be copper 2+ added to added to some electrons to make a solid, and the only solid we can have is the element with no charge. That's going to be copper solid. This is going to be aqueous, of course. Right, let's have a look. So I've got Cu before the arrow, Cu after the arrow. Balance, no problems. Overall charge on this side, 2+ plus 1-. So I've got 1+ overall before the arrow, 0 after the arrow. Therefore, it needs balancing. Put a great big 2 in front. Overall is balanced. So now I've got a balanced equation there. Then let's have a look at what's happening at the anode end. Then the anode end, we've got let's see the evidence at the anode, which is a positive. It says gas is given off. Now from this, it's the this species which will then give up the oxygen. So remember, oxygen is in group 6 on the periodic table. Now what happens then is oxygen there, O part of the hydroxide, will then make oxygen gas, diatomic again, there it is. And look what's happened is it's lost some electrons. Here we go. There they are. And in fact, let's do some balancing then. So I've got 1 O here and 2 O's here. So let's put a great big 2 at the front of this. The oxygens are balanced. The O's are balanced. Now let's have a look. Overall charge before the arrow, 2 times 2- is 4-. Here I only have 1-. Therefore, I'll just multiply the whole thing by 4. Okay, let's put some state symbols in our gas, and this will be aqueous. Right, it all seems balanced. 2 of those, 4. Yeah, over here, I've got 1 of those, 2 plus 2-. Yeah, 0 and 0. Right, all balanced, 2 half equations done. Incidentally, you may ask yourself, why didn't the H+ ion go to the cathode? Why was it the copper? Well, it's all to do with the affinity. If you think of the reactivity series, metal reactivity series, any metals under hydrogen, things like copper, silver, gold and platinum, titanium, all these useful metals, the metals that are used to make useful things, they like to be in the element state. So they don't want to lose any electrons or gain any electrons. They do want to gain electrons. They want to be in the element state. Okay, so they will gain electrons. They won't lose electrons. compared to hydrogen. So the affinity for these metals, they want to have those electrons more than hydrogen. So they will migrate or be attracted to the cathode to pick up those electrons from there. Compared to sodium, for example, sodium is higher on the higher up than hydrogen on the reactivity series, so it's above hydrogen. Therefore, its tendency is not to accept electrons. It's happy to be the sodium ion. Therefore, it'll let hydrogen go off to the electron and pick up those electrons. And that's really, really important in part of this revision. So let's go ahead and answer the questions. Let's see. So identify the gas given off at the anode. Well, we've worked out that it's going to be oxygen. Identify the solid made at the cathode. Well, the only metal around then that has high affinity for those electrons at the cathode is copper. So we'll get the solid copper being made there. And the right equations for both of these, we've done that in the breakdown. Let's have a look at the answers just to make sure. Excellent. Right. Thank you for listening to this. Please do like and subscribe if I've been helpful. Please do also share this with your friends if they need help with revision on either electrolysis or redox equations. Furthermore, if you need any help yourselves, please send me an email on sceinceclassnotes@gmail.com, and I'll try and get back to you if you need any help, if you have any other suggestions as well. Thanks for watching.